How does an eagle body arrange many parts together before flight, breath, vision, strength begin?
What hidden order keeps organs placed so signals, air, blood move without conflict inside constantly? Organs never float randomly. They fit tightly, leaving paths open for motion and flow inside.
This arrangement allows fast reactions when danger appears, without pause, confusion, or wasted effort inside.
The heart, lungs, stomach, nerves hold fixed places so pressure changes never collapse order inside. Even during stress, this inner map stays stable, guiding all later actions smoothly inside together. This organized foundation prepares the eagle body for all emergency functions that follow inside later.
Inside this organized body, tiny living units perform work that larger systems cannot handle alone. Cells join as groups, forming tissues that act together without needing thought or direction. Wing muscles rely on long cells that shorten together, creating controlled force during flight. Lung cells stay thin, allowing air contact without delay or blockage during breathing. Blood cells move freely, carrying gases and fuel through narrow paths efficiently.
Nerve cells stretch long distances, linking distant parts without breaking communication flow. Digestive cells release simple substances, turning food into usable parts for energy.
This silent cellular teamwork supports the larger body reactions described next.
Cells need coordination, so signals move fast, telling parts when to act or pause.
Inside the eagle, nerve paths carry quick messages using tiny electric changes along fibers.
These signals travel from eyes, wings, lungs towards central control areas rapidly.
Chemical messengers also move slowly, adjusting effort, timing, and strength across tissues.
Both systems work together, never competing, always supporting the same survival goal. Signal paths stay protected, so pressure or movement does not interrupt message flow.
This communication network prepares the body to sense the outside world next. The eagle body constantly gathers outside changes using specialized sensors placed throughout internal pathways.
Eyes convert light into signals, sending detailed information inward for immediate processing. Pressure sensors detect wind force, body position, and sudden movement shifts during flight. Chemical sensors inside air paths recognize oxygen levels and harmful particles quickly. Temperature sensors notice cold or heat changes, adjusting internal balance automatically.
Balance sensors track head and wing position, preventing loss of control mid-air. These inputs reach control centers, forming a live picture of surrounding conditions. Information updates continuously, never stopping, even during rest or soaring. During emergencies, sensing speed increases, reducing delay between change and response.
This incoming data prepares the body to manage breathing next.
Air enters the eagle body through openings that guide flow without turbulence or loss inside. Inside, air moves through firm tubes that prevent collapse during rapid breathing under high demand. Lung surfaces stay wide and thin, allowing oxygen contact across flowing air during every breath.
Oxygen passes into blood, while waste gases move outward simultaneously through thin exchange layers membranes. This one-direction flow keeps oxygen supply steady even during extreme effort and stress events.
Firm air sacs assist movement, pushing fresh air deeper each cycle without mixing waste gases. Efficient gas exchange supports heart delivery, which carries oxygen onward through vessels rapidly everywhere inside.
The eagle body uses branching vessels to move oxygen, fuel, and waste efficiently everywhere inside.
Strong central pumping pushes fluid forward, maintaining steady movement despite changing body positions.
Transport speed increases automatically when muscles demand more fuel and oxygen urgently.
This network stays flexible, bending safely as wings move and body twists during flight.
Pressure remains balanced, protecting delicate exchange areas from damage under stress. This moving network relies on a special fluid, explained next.
This circulating fluid carries oxygen, nutrients, signals, and heat throughout the eagle body continuously inside. It flows smoothly, adjusting thickness and speed based on temperature, effort, and emergency demand levels. Red cells bind oxygen securely, releasing it where working tissues signal urgent need most inside.
Other components transport nutrients, remove waste, and support repair during constant motion within the body. The fluid also spreads heat evenly, preventing cold or overheating during long flights inside systems.
Pressure stays controlled, so delicate vessels never rupture during sudden speed changes inside the body.
Chemical messengers travel within this fluid, extending communication. Loss of this fluid balance quickly disrupts oxygen delivery and energy availability everywhere inside tissues. This living fluid connects transport, control, and energy systems described next, internally within the body.
Energy enters the eagle body through food, taken quickly during short feeding opportunities.
Food moves into internal chambers where physical braking begins before chemical changes start. Simple fluids mix with food, separating useful parts from waste efficiently inside the system. Balls absorb small energy units, passing them into transport pathways immediately.
Useless material moves onward, never blocking the flow of useful substances. Processing speed adjusts based on hunger, activity, and current energy demand signals. During emergency flight, digestion slows while stored resources take priority for use.
This system balances intake timing with survival needs during unpredictable conditions.
This intake logic feeds directly into internal energy production systems ahead. Inside cells, energy units are released from nutrients through controlled chemical steps continuously.
This process produces usable power without heat spikes that could damage delicate structures. Energy is packaged into small units, ready for immediate use by working systems.
When demand rises, production speed increases smoothly without interrupting other processes. Energy availability prepares the body to maintain structure under force next. The eagle body relies on rigid internal supports to maintain shape during powerful movement. Bones form a light frame that resists bending while allowing controlled motion.
Hollow structures reduce weight without reducing strength needed for flight stress. Joints connect supports, permitting precise angles without grinding or instability.
Internal supports protect soft organs from pressure during dives and sudden turns.
This framework distributes force evenly, preventing damage at single points.
Supports anchor muscles, giving leverage for efficient power transfer. During emergency strain, Structure holds steady, while other systems increase output.
This stable frame enables controlled force generation described next.
Muscle tissues generate movement by shortening fibers when chemical energy triggers controlled internal reactions inside. Each fiber pulls against bones, converting stored energy into directed force efficiently during flight maneuvers.
Control signals adjust strength, speed, and timing to match current survival demands inside the body.
Opposing muscles relax as partners contract, preventing damage while maintaining balance during rapid directional changes. Heat produced spreads through circulation, avoiding localized overheating within active tissues during intense exertion periods.
Muscle fatigue is delayed by efficient coordination between fibers and energy systems during prolonged flow.
This force generation integrates with support systems, stabilizing the body under stress during emergency states. The eagle body constantly keeps internal conditions stable despite rapid outside changes during flight. Temperature stays controlled through blood flow adjustments and controlled heat release from muscles. Acid levels are regulated so chemical reactions continue without slowing or damaging tissues.
Pressure inside vessels adjusts automatically, protecting delicate exchange surfaces from stress. Sensors detect small shifts, correcting them before larger failures develop internally.
During emergencies, stability limits widen slightly, allowing stronger responses temporarily.
Stable conditions allow chemical regulators to guide longer control next.
These signals regulate growth, repair, energy use, and stress responses during prolonged emergency conditions periods.
This layer prevents overreaction, spreading effort evenly across systems under sustained demand during emergency states.
Chemical timing ensures recovery begins while action continues, avoiding collapse from exhaustion within tissues everywhere. Interactions between chemicals and nerves fine-tune priorities without conflicting commands during high-stress events.
This coordination stabilizes internal pace, as external danger remains unpredictable for survival during emergencies now.
Balanced chemical control supports defense, repair, and energy systems simultaneously across the eagle body now.
With regulation established, protective systems activate efficiently when threats damage tissues during emergency exposure events.
Protective barriers line surfaces, blocking harmful particles and organisms from entering internal spaces safely continuously. Inside fluids, roaming cells identify threats and react quickly before damage spreads widely internally further. These cells surround intruders, isolate harm, and begin cleanup without stopping other functions anywhere else. Protective responses scale carefully, avoiding excessive reaction that could disrupt normal operations inside the body.
Barriers repair small breaks quickly, restoring separation between internal and external environments for continued safety.
Energy and transport systems support defense efforts without starving other essential processes inside the body. Defense remains active silently, adjusting strength based on threat size and persistence within internal systems. Once danger lowers, defensive activity reduces, allowing repair systems to dominate responses across affected tissues.
Protection success enables detection and repair processes to proceed effectively next within the body systems.
Cells constantly check themselves for damage caused by stress, toxins, or mechanical strain.
When faults appear, repair tools activate, fixing small problems before they spread further. Damaged cells signal neighbors, coordinating repair without halting overall body function.
Severely damaged cells are removed carefully, preventing harmful contents from leaking internally.
New cells replace lost ones through controlled growth in affected tissue areas. Blood supply increases locally,
delivering materials needed for rebuilding structures quickly. Repair speed adjusts based on available energy and overall survival priority demands. During emergencies, repair may pause briefly, resuming once immediate danger passes. This repair capacity supports system coordination during continued stress events next. Control centers shift priority toward breathing, circulation, vision, and movement immediately. Signals redirect blood flow toward muscles and lungs, away from storage and digestion areas. Energy release increases where needed most, preventing failure in essential systems. Coordination prevents competing demands that could overload transport or chemical balance. This hierarchy changes dynamically as conditions shift during ongoing stress events. Once danger reduces, priorities slowly return toward balance across systems.
Understanding limits becomes essential as strain approaches critical levels next.
When demand exceeds capacity, small delays appear, reducing response speed and accuracy overall during emergencies.
These limits signal danger, forcing output reduction to prevent irreversible damage within vital internal systems. After emergency strain, systems shift toward restoring balance using stored energy and repair signals inside. Energy production reduces pace, shifting excess resources into reserves for future emergencies and long flights. Repair processes resume fully, strengthening tissues weakened during intense emergency activity across multiple internal systems.
Chemical controls adjust sensitivity, learning from stress patterns to respond better later during future events.
Some limits leave lasting changes, slightly altering performance and endurance over time within the body.
Is it? If recovery succeeds, overall function stabilizes, supporting continued survival in challenging.
This outcome closes the internal story of how an eagle body handles crisis events successfully.
All internal systems remain linked, constantly adjusting together as one coordinated biological network.
Breathing, circulation, energy, and control never act alone, always responding as a unified process. Small internal shifts are corrected early, preventing large failures from developing silently inside. Past emergency responses influence future reactions through lasting internal adjustments across systems. Efficiency improves where survival demanded repeated strong responses over time. Weak areas receive added support or reduced load to maintain overall balance. This integration allows the eagle body to function reliably across unpredictable conditions.
The internal story continues as long as coordinated function remains intact.